And make sure we don't have the same mistake we had last time. Got it. All right, part A, random variables. So we say they are functions of outcomes of random experiment. Assigning or that assign real values to each of the outcomes of the experiment. So we run a random experiment with a given set of possible values, and we define for each of the values of the outcome a function, x for that value. The notations that we'll be using, can I use C or W? Usually in an advanced class in probability, you always see X of W, things like that. So these are the outcomes of the experiment. So C or omega is going to be for outcomes of the experiment. And take any values in the sample space. And last time we defined the sample space as being the set of all possible, very important word, possible outcomes of the experiment. Then we went to the random variable x assigns to C or to omega. That's why you would see x of omega or x of C after an experiment. That would be the value of the random variable x that is assigned to the outcome C or W. And this is the point where most of the time people get lost in a probability class. Because after this, you start talking about random variables x, y, z, x plus y, and so on, and you forget where they actually come from. They come from the experiment, and the values of the outcomes of the experiments are the omegas, the C. This could be in an experiment of toss a coin, omega or C are H or T, head or tail. Those are the values of omega. They don't have to be numbers. They can be trees, people, anything. But when you go to x of C or x of omega, those have to be real numbers. Okay? Like I can run a random experiment in a forest where somebody goes and chooses trees, and to the value of each to each of the trees we assign a number. If you pick that tree, then you get 2. If you pick the other one, then you get 1. If you pick the third tree, then you get 2, and so on. Right? So the tree is omega, and x of omega is the number that you assign. And so when we do this, we will say the probability that x is equal to c. Remember that there is no probability that is defined for x. The probability was defined for the outcomes of the experiment, right? And now, because x depends on that outcome, we will extend that probability now to go define it for the values of x. So usually you will see in a book, we'll say probability px that x is equal to c. What is it equal to? It is the probability of the set of all outcomes such that the value of x for the outcome is equal to x. That's actually what it means. And this p is the probability that we have been talking about. Probability of the outcomes of the experiment that I defined. But prior to this definition here, you don't know what this is. Now, example, toss the coin twice and define x equals the number of heads. So toss the coin twice and define x equals the number of heads, for example.
In point P, was not this C fixed on the left hand side?
What?
I guess this C was fixed on the left hand side. In point.
No, that's not C. Sorry, that's x. A probability that x equals little m. Otherwise, there will be no. We don't know what x is here, right? So if you toss the coin twice and you define x to be the number of heads, this x is a number. It's a real number. In this case, it's even an integer, right? So that's the random variable that is defined on the outcomes, which are heads and tails. Does that make sense? So x is a random variable. With possible values. What are the possible values of x? The number of heads could be 0, 1, or 2, right? So those are all the x's. And probability I'm giving the example to explain this definition that is written here. So probability on the x that x is equal to 1 is equal to the probability of the set of all c's. So let me call C result, the result of the experiment, okay? Such that, what is x defined as? Number of heads, right? such that the number of heads in the result is equal to 1. That's what that definition is. So what is the probability that x is equal to 1? It's the probability of the set of all results of this experiment for which the number of heads in the result is equal to 1. And now you can write down what that is, taking into account what the result is supposed to be. The result would be head, 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 tail, tail, head, or tail, tail, right? So here, that would be that this probability is the probability of head, tail, tail, head. These are the only outcomes, the only results for which there is exactly 1 head. Does that make sense? Okay. So this is how you get this definition in practice. Is there any question? All right, we could define y equals five if head, head, 2 if head, tail, 1 if tail, head, and 0 if tail, tail. That's also another random variable that is defined on the outcomes of this experiment. It's also a random variable. So probability that y equal 5 is equal to the probability under y that y is 5 is equal to the probability of having head, head. Probability under y of having y equals 0 is probability of tail, tail, and so on. That's what it is. So you can have one experiment and have a bunch of random variables that are defined on that same experiment, depending on what you are interested in. Right. So B, now we have to make a difference between the discrete and the continuous. Discrete random variables. Definition. We say that the random variable is discrete if it takes not more than a countable number of values, which means finitely many or countably many. So we say that a random variable x is discrete if and only if x takes finitely many values or countably many. Or you can say at most count. So you don't want to have a random variable that takes values in the entire interval from 0 to 1 and you think it is discrete. That's not a discrete random variable. Example 1, and these examples now are very important. They are specific distributions that we will use later on in this class. Example 1, Bernoulli. Bernoulli random variable. So we say that X follows Bernoulli distribution with parameters n and p. If and only if the probability that X equals 1 equals 1 minus the probability that X equals 0 equals p. Sorry, here you don't need n, so just the Bernoulli with parameter p. And probability that X equals C equals 0 otherwise. So anywhere else, the value of the probability is 0, except for 2 points, 0 and 1. Usually 1 is assigned to what we call success, and 0 is assigned to failure. So this random variable doesn't always start by 0 and 1, okay? So 0 and 1 can just be assume some notations. You can run an experiment, any experiment that has only 2 possible outcomes. When you choose one of them to call success and the other one failure, and you define the random variable that gets value 1 for success and 0 for failure, you get the Bernoulli random variable. Okay. Here, P is the parameter of the distribution. When it's known, they ask you what's the probability that X is equal to 1. If P is 1/2, then it's 1/2. If P is 1/4, then it's 1/4. Right. Binomial random variable. So we say that X follows, and this is where the n comes in, binomial and with parameters n and p, if and only if the probability that X is equal to K is equal to choose K out of n, take p to the power K, take 1 minus p to the power n minus K. For K equals 0, 1, all the way to n. And P of X equals C equals 0 otherwise. So for any other points, the value of the probability is 0, except for integers between 0 and 1. This random variable, as we will see later, is related to the first one. In fact, you obtain a binomial random variable by running a Bernoulli random variable n independent times and adding the number of ones or adding the number of successes. The random variable that assigns to that experiment the number of successes has this distribution, which is called the binomial distribution. This choose k out of n is what we denoted when we were doing counting. It is the number of combinations of k out of n, which is n factorial divided by k factorial times n minus k factorial. This is what that notation is. And intuitively, it's understandable if I'm telling you that you obtain x by adding n independent Bernoulli random variables, and you want to find the number of successes, then that will be the sum. If you want that sum to be k, that means you want to have k successes out of n experiments, and you don't know which one of them are going to be the successes, right? And it doesn't matter the order that you're taking. That's why you choose k possible successes out of the n positions that you have, and you don't order. Does that make sense? Huh? No, that's an explanation of why the formula. In a question, you have to apply the formula, right? Now I'm explaining why you have this formula. Okay. When you have a problem, all you need to do is plug in the numbers and see what this is equal to. Okay. And when we get to the part where we prove that the sum of n independent variables like this gives you that, that's a different problem. At that point, you will need to prove it the way I will show you there. We are not there yet. Okay. We are getting slowly there. So here, for instance, inside that example, we could say we take binomial 3, 1/4, which means n is 3 and p is 1/4. Probability that x equals 0 equals, that's k 0. So n is 3, so that's choose 0 out of 3. Take 1/4 to the power 0, and then take 1 minus 1/4 to the power 3 minus 0. That's what it is. And so choose 0 out of 3 is 1. There's only one way to take nothing out of 3. Then 1/4 to the power 0, anything to the power 0 is 1. So you get 3/4 cubed. So that's the probability of having x equals 0 for a binomial 3, 1. Probability that x equal 1 is choose 1 out of 3, then take 1/4 to the power 1, 1 minus 1/4 to the power 3 minus 1. Choose 1 out of 3. There are 3 ways to choose one thing out of 3. So that is 3 times 1/4 to the power 1, that's 1/4, times 1 minus 3/4, 1 minus 1/4, that's 3/4 cubed. So the answer is 3/4 to the power 4. If you want probability that x equals 2, that is choose 2 out of 3. 1/4 to the power 2, 1 minus 1/4 to the power 3 minus 1, 3 minus 2, sorry. And then you do the computation. There are 3 ways of choosing 2 things out of 3. You write down that formula and develop, you see that choose 2 out of 3, that's 3. So you get 3, then 1/4 squared, and then 1 minus 1/4, that's 3/4 to power 1. So that's times 3/4. So that gives you 9 out of what? 64. Then you go probability that x equals 3 is going to be choose 3 out of 3, 1/4 to the power 3 times 1 minus 1/4 to the power 3 minus 3. That gives you choosing 3 out of 3. There's only one way. This is 0 times 3/4 to the power 0, 1. So you get 1/4 cubed, which is 1/64. And for any other value, probability that x equals c equals 0. Okay, it's 5 in 0. So if I take any number other than 0, 1, 2, 3, in this case, the probability to have that number is 0. Any questions? Now, based on this, there's what we call, after defining the random variables, you have what we call the cumulative distribution function. Which is defined as f(x), let's say distribution of x, of little x equals probability under x that capital X is less than or equal to x. And this definition does not depend on the type of random variable. Whether it is continuous or discrete, it doesn't matter. Any type of random variable works with that formula. So if we take this example here, if we take the example that we have up here, capital F(x) of -1 is 0 because there is no value of this random variable below -1. The values start 0, 1, 2, 3, and so on. So the value of the cumulative distribution at -1 would be 0. If I take at 0, that's going to be probability that x is less than or equal to 0. And for that random variable, there is only one value that is less than or equal to 0, which is 0. That's why it is equal, in this case, to probability that x equals 0, because it's the only value that satisfies that inequality. And the probability that x equals 0 is 3/4 cubed. So that's why this is 3/4 cubed. Are we good? If we continue on that same example, we will find if I want f x of 2.5, what is it equal to? Huh? 0, 1, and 2. Why? Because this is probability that x is less than or equal to 2.5. And at this point, you shouldn't be confused because the definitions of the probabilities were saying that for the integers 0, 1, 2, and 3, you don't have 0, but anything else is 0, right? But the cumulative distribution is defined for any number, not just those 4 numbers that are in the range of the random variable. So anytime you have that, you need to write down the definition first, and then you count, as said in this definition here, that I gave you here, you count all the outcomes that satisfy the given set. And all the outcomes that satisfy this set, those are probability that x is equal 0, plus probability that x is 1, plus probability that x is 2. I can have 2.5 because x cannot be 2.5. And so we add those numbers and we get the answer. So that's going to be 3/4 cubed plus 3/4 to the 4th plus 9/64. So that's the probability. And if I want probability, say f x of 4.98, that is probability at x. I'm choosing some pretty crazy numbers here to put just for you to understand that you need to take care of the values that are in the range of x. That's all that matters, okay? That x is less than or equal to 4.98. And then you count the things that are less than 4.98. Guess what's going to happen? What are the values of x that are less than 4.98? Huh? Is it? There is one word for that in this class. What is that? Huh? The sample space. Is the entire sample space. That's probability of s, and we know it's 1. So I don't even need to go write it down and add. So if I want to find the values of x that are less than 4.9, it's the whole sample space in that problem. So no need to write down the probabilities and add them because I already know that the probability of the sample space is 1. Okay. All right, so let's move away from this one. If everybody is happy, then I'm happy. Any questions before I move to the other piece? And the next piece is going to be continuous random variables. So we say that a random variable is continuous if and only if its cumulative distribution function is a continuous function. So if that cumulative distribution function, which is this function that we have been working with in the example, okay, if this f of x that we define here, right there, if that f of x is a continuous function, then we say that the random variable that we are dealing with is continuous. Of course, that means that for the example that we had before, it is not continuous, right? Because it's a discrete random variable. It has only finitely many values. Is a continuous function at all points of R being the set of all real numbers. Now, usually the confusion is with the next one. The random variable is absolutely continuous. That's the extra word. If and only if the cumulative distribution function can be written as integral from negative infinity to x, fx of t dt for some function fx of t called PDF, which is probability distribution function. In this case, in this specific case of absolute continuity, the derivative is equal to that probability distribution function. So now we have two things defined: a probability distribution function and a cumulative distribution function. The derivative of the cumulative distribution function, the derivative of the cumulative distribution function is equal to the probability distribution function when the random variable is absolutely continuous. If it's not absolutely continuous, then this derivative might not even exist at some point. For instance, when this function is not continuous, the notation derivative makes no sense, right? So, an example here. What we call the uniform distribution of A, B. little f(x) of x is equal to 1 over b minus a. So here b is larger than a. That's the only condition. It could be negative both, or one negative, the other one positive. It doesn't matter. So times I a less than or equal to x less than or equal to b. This is what we call the indicator function of the set A. Okay? Where a less than or equal to x less than or equal to b equals 1 if x belongs to the interval AB and 0 otherwise. That's what we call the indicator function of the set of the interval from A to B. A function that assigns 1 to every number that is on that interval and 0 to anything else. It's just like indicating, yes, this number is here. All right. Okay. So which technically means that this function is equal to 1 over b minus a for any x inside the interval equal to 0 elsewhere. In this case, capital F x of x equals if x is less than a, then 0 for x strictly less than a. If we don't move up to a, then we haven't started touching the random variable yet. Therefore, the CDF, the value of the CDF is 0. Once we cross a and we start moving towards b, if a is less than or equal to x less than b, then we start touching the interval from a to b. And notice that here, b minus a is actually the length of the interval from a to b. So what is on top, the probability to hit any subset of that interval, because it's uniform, it's just going to be the length of the given interval. That's why the top is going to be x minus a, which is the length of the interval from a to x. Does that make sense? So this is x minus a over b minus a. Which is also obtained by taking the integral of this from a to x. Because you take the integral from negative infinity to x, but from negative infinity to a, you have 0. So it's just integral from a to x, which is x minus a. And then when x is larger than or equal to b, this thing is going to be 1. Because after b, there is nothing else that is happening. So the value of the function will remain same as it was at b. And at b, when you plug in b for x, you get b minus a over b minus a, which is 1. So that's the reason why this is the CDF of the random variable that is uniform on the interval from a to b. And you can check that fx prime of x equals little fx of x. So x is absolutely continuous. So this is an example of absolutely continuous random variable. Any questions? So, my dear friends that are online, please tell me, does this make any sense? I see Rachel smiling. So, Rebecca, does it make sense?
I was confused where you got the x minus a over b minus a. Can you go over that again?
Right, thank you. So, fx of x is integral from negative infinity to x of fx of t dt. And fx of t, that's integral from negative infinity to a fx of t dt plus integral from a to x fx of t dt. But we said that a is less than x and less than b, right? So from negative infinity to a and fx of t equals 0 for t less than a. So this piece is 0. Fx of x is therefore 0 plus integral from a to x. And between a and b, the little fx is 1 over b minus a, so dt. Don't be afraid to ask a question. When you ask, I will explain. If I don't explain, it's because I think you know, you understand. So now you integrate this, which is t over b minus a, plug in a, then plug in x. And that gives you x minus a over b minus a.
Thank you. That makes sense where that came from now. It's been a while since I've seen integrals.
Thank you. Just don't be afraid to ask a question. I need your question to know if you understand or not. Otherwise, I'll just be rolling thinking that it's okay. All right, anything else? Any other questions? Okay. Now, if there is not a question, let me see what I can do. Remark, for a continuous random variable, probability that x is equal to a is equal to 0. So when you have a continuous random variable, you can have the probability to hit a single point. That's kind of saying, if I ask you to shoot a given point on this board and I put a point there, then the chance that you will hit that point is 0. Why? Because that board has more than countably many numbers. There's somebody pointing something in your face here? I see a red point on your face. All right. I was saying, do we have snipers in this classroom now? All right, so this is the case here. And for a discrete random variable, on the contrary, the probability that x is equal to a is equal to the value of the CDF minus the limit of the CDF when x goes to a from below. What this means is the limit as x goes to a from below. Okay? That's what we call a minus, no one, but a minus. Where fx at a minus is limit as x goes to a and x is less than a of fx of x. And you know, when the function is not continuous, this limit is not equal to the value of the function, right? You know that the condition for a function to be continuous is that the limit on the left is equal to the limit on the right. But this value here is the limit on the right. And if you know that the function is not continuous, then this is surely not equal to the limit on the right, because this is the limit on the left. Right? And it says the difference between the two gives you the value of the probability at this point. Now we can take an example to illustrate this. Let's say we have x follows Bernoulli with parameter 1/3. Okay. What does this mean? It means that probability that x is equal to 0 is 1 minus 1/3, that is 2/3. And the probability that x equal 1 is 1/3. That's the definition that I gave you earlier. That the probability that x is equal to 1 is p, and the probability that x is equal to 0 is 1 minus p, which is 2/3 in this case. Moreover, probability that x equals c equals 0, otherwise, no matter what you take as any other value, the probability is 0. Now, what is f(x) of x equal to? For any x strictly less than 0, because 0 is the smallest value of that random variable. If we take any x strictly less than 0, fx of x is 0, right? Because we haven't started touching the variable yet. So for 0 less than or equal to x strictly less than 1, if x is strictly less than 1 but larger than 0, then fx of x is just probability that x is equal to 0. That's the only value. That's the only value of the random variable that is here, right? Between 0 and 1, excluding 1, there's only one value. So the value of the function is going to be 2/3. For any x in this interval, the value of the function at x is 2/3. Now, for any x larger than or equal to 1, notice that I didn't include 1 here, right? Now, for any x larger than or equal to 1, what happens? Fx of little x equals, what's going to happen here? Huh?
Gonna equal 1/3.
Now, how many values of x will satisfy probability that x is less than little x or equal if little x is larger than 1? Let's go. What is equal to 1? The value of x or the probability? The probability is 1 because if little x is already larger than 1, that means it's greater than all the 2 values of the random variable. So it's the probability of the whole space, right? And that's why it's equal to 1. Now, knowing this, what this formula here says, because in some problems, they might just give you the CDF, okay? And they ask you for the probability of some points where you have some jump, where you have some jumps in the graph of the CDF. The probability of those points are obtained by using this formula that I'm giving you here. So you find the left, you find the right and the left limits, and you subtract them, and you see what the jump, the size of the jump there is what the probability of that specific point is. Okay. So I'm going to do that here. How many jumps do we have in this function? Huh? Two. One at 0, one at 1. The number of jumps is equal to the number of discrete points that you have that have masses in the random variable. Okay. So here we have 2 jumps. So there are 2 such points where we might be interested in finding the probability that x equals 0 or x equals 1. If we did not know this, and we had only this CDF, so this is the CDF that is fully defined here. It has 3 values: 0 if x is less than 0, 2/3 if x is between 0 excluding 1, and 1 if x is larger than or equal to 1. If I want to find probability that x is equal to 0, what that formula says that is that it's fx of 0 minus fx a minus, which is 0 minus, which is equal. This means, what's the value of the CDF at 0? Based on this one. Huh? 2/3. You shouldn't be afraid to say what you know. Okay? Why is it 2/3? Because 0 is here. 0 is in the second, not in the first. 0 is in the second interval. So the value of f at 0 is 2/3 minus the limit, as I said, this is limit of f of x as x goes to 0 but is less. When x goes to 0 but is less, where is it? Here. When it goes to 0, the value of f of x is 0. So on the left, that probability is 0. And that's why you recover what you knew from the beginning, that the probability that x is 0 is 2/3. Okay. Does that make sense? All right. And you can do that for 1 as well. For 1, you will have 1 as f of 1 minus 2/3 as the limit from below. That is 1/3 equal to f of 1. Now we do what we call transformations. Random variables. Discrete case, how do we find the probabilities for a transformation of a discrete random variable? The question can be find the distribution, find the TDF, also the TMF, because when it's discrete, we call it TMF, probability mass function. So PMF stands for probability mass function of y equals T of x. And then how do you find that? What you do is probability that y is equal to little y. To find the PMF of a random variable, you have to find the value of the probability for each of the possible values of, yeah. What's that? Oh, yeah, I couldn't see that, sorry. So I was saying to find, if the question is find the PMF of a random variable, which is discrete, it means find the value of the probability of each of the possible values of that random variable. So here, if y is a possible value of that random variable, how do I find the probability? I write that as probability that y is g of x equal to y. And I know the values of x and their probabilities. So after writing this, I don't need to worry too much. What I need to do is to complete this work, apply g to all values of x and regroup them by possible values of y then assign the sum of probabilities as answer, which means what? Let's say we take the, as an example earlier. Okay, we had the example of the binomial 3, 1/4, where we had probability of 0 if x equals 0 equals 3/4 cubed. Probability that x equals 1 was 3/4 to the fourth. Probability that x is 2 was 9/64. And probability that x is 3 was 1/64. And I'm going to define y equals x squared minus x. So this is the random variable y, and the question is find the PMF of y. So what we do is we take, this is g of x, right, which is x squared minus x. And so the possible values of y are when x is equal to 0, y could be 0 squared minus 0, which is 0. When x is 1, y will be 1 squared minus 1, which is 0. And when x is 2, y will be 2 squared minus 2, which is 2. So what this whole text here was saying is regroup the options by values of y. How many values of y did we get? How many possible values of y did we get in it? 2, 0, and 2. So we group the answers by values of y. So that's 0 and 0 here. So when x is 0 or x is 1, that's one value of y. So we would say probability that y equals 0, we will group all the values of x that answer for that.
Why are we not using 3?
What?
Why are we not using x is equals to 3?
Oops, I didn't check that. I'm stopping here. I didn't see that, guys. So x equals 3. You're right. This one is there. 3 squared minus 3 is 6. So we do have three values. And so probability that y is 0 is going to be for x equals 0 or x equals 1. So and that is going to be 3/4 cubed plus 3/4 to the 4th. And then the next value of y is probability of y equals 2 equals, and there is only one x that answers for that. And probability that x equals 2, and probability that x is 2 is 9/64. And then the third value of the probability that y equals 6 equals probability that x equals 3, which is 1/64. And probability of y equals c equals 0 elsewhere or otherwise. You understand? For any other value of c. So we got the PMF of y. Usually we can put that in a table. For y, we got 0, and we can add these numbers. It's not that important. So it's going to be 3 cubed plus 3 to the 4th over 4 to the 4. Got 2, 9/64. And then one is a 6. So this is the PMF of the random variable y. And based on that, you can construct the CDF of y. And based on that, you can answer all the questions concerning y. Okay. That's the case when the variable is discrete. But when the variable is continuous, sometimes it becomes complicated. Sometimes it's easier. So continuous random variables here to find probability distribution function of y equals g of x. What you do is you write probability that y is less than or equal to y. Notice that now here I have probability that y less than or equal to y, no more equal, because the probability that capital Y is equal to little y is 0 when the random variable is continuous. And this is equal to probability that g of x is less than or equal to y. And to solve, you need to solve for x to obtain inequalities in x to compute the probability. That's what you would do in general if you just have any function there. So, but if we do have that the function g is 1-to-1 and differentiable, then you would have that the probability that y is less than or equal to y is equal to probability that g of x less than or equal to little y, which is equal, and here I'm assuming that it's 1-to-1, but it's increasing. If it's decreasing, you have the opposite inequality, okay? If it's increasing, then this is equal to probability that x less than or equal to the inverse function at y. And we know this is the CDF, that's the formula of the CDF, so that is fx of g minus 1 of y. That's how you would do in that case if the function g is 1-to-1 and increasing, and the little fy of y, which is the PDF, in this case is going to be equal to little PDF at g minus 1 of y times dx over dy in absolute value. This is in general. And you obtain that by taking the derivative here, because you know that the join the CDF, to get the PDF from the CDF, you take the derivative. So this is the CDF of capital Y. I take its derivative, I obtain the PDF of capital Y. And taking the derivative, you have a chain rule. That's why you have this piece coming here. That's it. And it seems we are the end of the time. Any questions? Is there any question? If not, thank you for your time. I'll see you next time.
Dr. Longlet, when you're writing, how are we supposed to know the difference between a capital X and a little x? Okay, and then
One
what's
of one of them is cursive, one of them is a capital letter. So
okay. And then when you're using the P and then the P with the extra stick, like how do you know when that's appropriate? Because you went from
the